Let's prepare to solve this problem. And by preparation, we're going to do this. We're going to take a look at the problem, try to wrap our mind around it, see what it's talking about. We'll gather together necessary variables and information, think about how we're going to model it, how we're going to solve it, and then we'll move forward to our solution. We'll start with the preparation. Okay, this is a question about an alligator. And it starts the morning at a temperature of 25 degrees Celsius and needs to warm up to a temperature of 30 degrees Celsius. Well, you and I keep our body temperature constant by using metabolic energy, but an alligator doesn't do that. And we're assuming this particular alligator warms itself up by getting energy from the sun, and it's getting it at a rate of 1200 watts, or 1200 joules per second. Okay? So the energy that the alligator absorbs from the sun, the change in energy, and that's going to be its change in thermal energy, is just equal to the power times the time. It's receiving 1200 joules per second. So the thermal energy it's going to receive is 1200 joules per second times the time interval in seconds. Okay? So we need to know how much is the time in order to give the alligator enough energy to raise its temperature from 25 degrees to 30 degrees. Well, this is basically a specific heat problem because we know the amount of energy that it takes to change something's temperature is this. The change in thermal energy is just equal to the mass times the specific heat times delta T. Okay? So we're going to add thermal energy at this rate. As we add thermal energy, the temperature is going to increase. How much time is necessary to produce the desired temperature change? Now let's go ahead and put some variables in here. Okay? The power we know is 1200 joules per second, so that's set. The mass is the mass of the alligator. That's 300 kilograms. Delta T is the change in temperature. Well, the change in temperature, 25 degrees Celsius up to 30 degrees Celsius, is a difference in temperature of 5 degrees. And we can put that in Kelvin. Okay, that's 5 Kelvin. Because if I take a difference in temperature, delta T, that's 5 degrees Celsius, but it's also 5 Kelvin. Since it's a difference, the scale factor between Celsius and Kelvin cancels out. Okay, so we have a 5 Kelvin change in temperature. How about C? What is the specific heat of an alligator? Well, there's a table in the book where you're given the specific heat of the mammalian body, okay? And we're assuming that for a reptile, it's about the same as the specific heat of the mammalian body. And so it's 3,400 joules per kilogram per Kelvin, okay? So we have all the data that we need. We've collected all the pieces together. Now what we're left with is putting the numbers together and completing our solution. And we'll do it this way. M times C times delta T, that's the change in thermal energy of the alligator, is just equal to the power times the time interval. And now we can put in all of our numbers. The power is 1200 joules per second. The mass of the alligator is 300 kilograms. The specific heat is 3,400 joules per kilogram per Kelvin. The change in temperature is 5 Kelvin. The only thing we don't know in this relationship is delta T. And so we can solve for it. If we do that, if we solve for the change in temperature, we get 4,250 seconds. But let's round that. And also I'm going to convert it to minutes. And I'm going to keep it to 2 significant figures because really this looks like maybe even a 1 significant figure problem because we have 5 degrees change in temperature, but that seems a little bit stingy. So we'll keep it 2 significant figures. I end up with 71 minutes, just over 1 hour. And is that reasonable? Because we need to think about that. The final stage of any problem is to assess it. 71 minutes is a bit over an hour. And if you've ever watched alligators, in the morning, they take their time getting ready. And it's cooled off pretty significantly overnight. On the other hand, we don't end up with a time that's like more than 24 hours. It's not more than the alligator can build up during the course of a day. So this seems quite reasonable. This seems like a good result. It matches our expectation of how the world works. And that's our final step in any problem is to check that.